lecture I am going to discuss the classification of the partial differential equations, and then I will try to solve the boundary value problems using the separation of variables method. So classification of partial differential equation. Consider the partial differential equation plus some function of x, y, z, p, q, where your capital R, S and T are function, are even continuous function of x and y, and R means your usual notation, del 2 del 1 del x2, S means del 2 del 1 del x del y, and T is del 2 del 1 del y2. So if this is your partial differential equation, say number 1, then at point x comma y, the PD1 is first point elliptic, or you can say hyperbolic, if your s square minus 4rt is greater than 0. If s square minus 4rt is greater than 0, then we will say that this equation number 1 is hyperbolic, and it is parabolic if s square minus 4rt is equal to 0, and this is your elliptic if your s square minus 4rt is less than 0. So at this point we will say that this partial differential equation is hyperbolic if s square minus 4rt is greater than 0, and it is parabolic if s square minus 4rt is equal to 0, and it is elliptic if s square minus 4rt is less than 0. And let us consider the example. Say we have the differential equation, partial differential equation at 2uxx 4 times uxy, and say 2 times uzz equal to say 3u. Now here you can see that your capital S is 4, your R is 2, and your T is again 2. So therefore it will be your uyy, not uzz. Therefore your s square minus 4rt will be, now s square means 16 minus 4 times r is 2 and t is 2. So you can see that again this is your 16 minus 16. So as it is equal to 0, so we can say that the partial differential equation is, hence the PD is parabolic. So the nature of the partial differential equation is parabolic. Now here we have only two variables, x and y. Suppose that we have three variables, say x, y and z. In case of three variables, consider the PDE. Say this is your PDE. Suppose that I is from 1 to 3, j is again from 1 to 3, a ij del 2 say u upon del xi del xj, then say some another coefficient from I equal to 1 to 3 and ai, or you can say bi, then del u upon del xi plus some function of plus some d into u equal to 0, or c into u equal to 0. Now if this is your partial differential equation, and here you can see that we have three variables, because we have the three values of I and j, so we will get three different variables. Now this partial differential equation also, here the matrix Aij, where my I is from 1 to 3 and j is from 1 to 3, is real and symmetric. Here the matrix is real and symmetric because we have just A11, A22 and A33. That means it is real and symmetric. A12 is same as A21, A23 is same as A32. So this matrix real and symmetric. Now this partial differential equation, now 1 is said to be the first point parabolic if the determinant of A is 0. If this equation 1 is said to be parabolic if your determinant A is 0, where my A will be coefficient of say ux11, then coefficient of ux12, coefficient of ux13. That means this will be your del 2 upon del x1 square. This will be your del 2 upon del x1 del x2. This will be your del 2 upon del x1 del x3. Then coefficient of del u x21, coefficient of ux22, ux21, ux22, then coefficient of ux23, then coefficient of ux31, coefficient of ux32, and then coefficient of ux33. So that means we have to take the coefficient of ux11, say del 2 upon del x1 square. So that will be a coefficient here, and then del 2 upon del x1 del x2, the coefficient of del 2 upon del x1 del x2 will be here, and so on. So now if the determinant of this matrix is 0, then we will say that the nature of the partial differential equation is parabolic. And PDE is hyperbolic if all the eigenvalues of A, if PD is said to be hyperbolic if all the eigenvalues of A are non-zero and except one are non-zero, have same sign except one. If all the eigenvalues of the matrix A are non-zero, if the eigenvalue will be, if one of them is 0, then determinant will become 0, and that case will become the parabolic case. So if all the eigenvalues are non-zero and have same sign except for one value, then the PD is said to be hyperbolic. Now PD is said to be elliptic if all the eigenvalues of A are non-zero and have same sign. So if all the eigenvalues have same sign and are non-zero, then this partial differential equation is said to be elliptic. Now let us solve questions. So classify the following PD. Classify the following PDs. The first one is, so classify uxx plus uyy equal to uzz. Then the second one is uxx plus uxy. I think we have uyy. Then we have uzz, then uyz, and then uzy equal to 0. And then third case uxx, uyy, uz equal to 0. So that means you can say that it is your Laplace equation. And then the fourth one is del t upon del t2 equal to c square del t upon del x, which is your one-dimensional wave equation. So first part, here you can see that the coefficient matrix, this equation can also be written as uxx plus uyy minus uzz equal to 0. So the coefficient matrix will be, now the coefficient of uxx is 1 and then the coefficient of uxy is 0. Again the coefficient of uxz is 0, coefficient of uyx is again 0, coefficient of uyy is 1, coefficient of uyz is 0, and then we have this one. So here you can see that if you evaluate its eigenvalues, a minus lambda I will give you 1 minus lambda 0 0 0 1 minus lambda 0. So now the eigenvalues of this matrix will be, now this is your characteristic equation. So eigenvalues are, so your eigenvalues are lambda equal to 1, comma 1 and minus 1. Here you can see that there is change in sign in the eigenvalues. So this means your partial differential equation is hyperbolic, because for elliptic all the eigenvalues should have the same sign. So this is your hyperbolic partial differential equation. Then for the second part was uxx, uyy, then it was your uzz plus uzy, and then finally uyz plus uzy equal to 0. So here the coefficient matrix is, the coefficient of ux is 1, uxy is 0, uxz is 0. Coefficient of uyx is 0, uyy is 1, uyz is 1. Coefficient of uzx is 0, uzy is 1 and uzz is 1. So now here you can see that as mod of a is equal to 1 times 1 minus 1, then 0, then 0. So you can see that as the determinant of the matrix A is 0, this implies that PDE is, your partial differential equation is parabolic. So the nature of the partial differential equation is parabolic. Then next problem was the Laplace equation, uxx, uyy, then uzz equal to 0. Here again our matrix A is 1 0 0 0 1 0 0 0 1. So determine A minus lambda I. Therefore determine A minus lambda I is equal to 1 minus lambda 0 0 0 1 minus lambda 0 0 0 1 minus lambda. So this is equal to 1 minus lambda cube. So here you can see that all the eigenvalues are lambda equal to 1 comma 1 comma 1. So as all the eigenvalues are non-zero and have same sign, this implies that PDE is elliptic. Hence the partial differential equation is of the elliptic nature. Then now the fourth part, which was your del 2 upon del t2 equal to c square del 2 upon del x2. So this can be written as c square del 2 upon del x2 minus del 2 upon del t2 equal to 0. So here your r is c square, your capital S means the coefficient of del x del t is 0 and your capital T is 1 minus 1. Therefore s square minus 4 rt is equal to 0 plus 4c square, which is always greater than 0. So this implies that one-dimensional wave equation is hyperbolic. So this is the nature of this one-dimensional wave equation. Now let us solve partial differential equations using the variable separable method. And I am starting with the problem. To solve the solution of boundary value problem, using the separation of variable method. So let us solve the problem number 1. Solve boundary value problem ux equal to 4uy. For the first case, when your u0y is equal to a times e power minus 3y, and for the second case, when your u0y equal to a e to power minus 3y plus 4 e to power minus 4y, 5y. Solve your this boundary value problem for these two conditions. So solution, first part, ux equal to 4 times uy. As here you can see that our u is a function of x and y because it depends on small x and small y. So let the solution of 1 is, say, u equal to some capital function capital X, which is your function of small x, into y, which is your function of small y. Let us assume u as a solution of this x into y. We can also write it as simply x into y. Then your ux will be the partial differentiation of u with respect to x will be the differentiation of x, and the differentiation of x means, say, x dash into y. Y will be constant, and the differentiation of x with respect to small x will be your x dash. Similarly, your uy will be your x into y dash. Therefore, by 1, we have x dash into y equal to 4 times x into y dash. So from here we will have x dash upon 4x equal to y dash upon y. That means we have separated the variables. Let us assume their common value as small k. So from here we will have x dash minus 4x k equal to 0 and y dash minus ky equal to 0. Now x dash can be written as derivative of capital X with respect to small x. Say this is your dx, where d stands for the partial differentiation with respect to x. And similarly here we can write it as d dash of y equal to 0, where d dash stands for the partial differentiation of capital Y, the partial differentiation with respect to y. So therefore, from here you can see that your auxiliary equation will be m equal to 4k, or you can see that your root is m equal to 4k. From here we will have m equal to k. So the complementary function will be c1 e to power 4kx. So that means here your CF is the final solution, because in the right hand side we have 0. So your x will be c1 e to power 4kx, small x, and then your y will be c2 e to power ky. Therefore your solution is u equal to x into y, which is your c1 into c2 e to power k 4x plus y. Or we can also write this c1 into c2 as another constant. Therefore your u equal to a times e to power k times 4x plus y. So this is the common solution for the both parts. Now for the first part, my boundary condition is u0y equal to a e to power minus 3y. So if you put x equal to 0 here, so this is your 2 by 2. If you put x equal to 0 and y equal, and if you put x equal to 0, then we will get the value of u0y as 8 e to power minus 3y, and in the right hand side we have a into e to power ky. So from here you can see that your a is 8, and k is minus 3. Therefore solution is So your solution will be 8 times e power k is minus 3. So in the bracket we have 4x plus y. So this is your solution for the first part. So hence it is our solution. Now for the second part, solution of second part. Now for the second part, now as this is your solution of equation number 1, and we know that the superposition of the solution will again our solution at u equal to a e to power 4 k 4x plus y is solution of 1, and we can also write it as b k 4x plus y is also solution of 1. This will be also solution of 1. So hence their sum is again a solution. If their sum is a solution, now here we can replace this constant k1 by k2. So this is your solution. Again, if you take the constant as k2 and the constant ab as another constant b, then this is again solution. Now as we know that the sum of two solutions is again a solution of this one, so let hence u equal to a e to power say k1 4x plus y plus b e to power k2 4x plus y is also solution of equation number 1. Now if this is your solution of equation number 1, then use the boundary condition. Now because our u0y equal to, because our u0y was h into e to power minus 3y plus 4 into e to power minus 5y. So let us put, therefore by 1, say this is your equation number 2. So by, we have already assumed 2, say it is your 3. Now if we put x equal to 0 here, then by equation number 3 we will have, in the left hand side we will have 8 e to power minus 3y plus 4 e to power minus 5y, and then the right hand side we will have a, as our x is 0, so this will be your e to power k1y plus b e to power k2y. So from here you can see that our a is 8, k1 is minus 3, and then your b is 4 and k2 is minus 5. Thus our solution is, therefore solution is u equal to a is 8 e to power minus 3 4x plus y plus b is 4 e to power minus 5 4x plus y. So this is your solution. Zxx minus 2 zx plus zy equal to 0. Now let us solve this question. So solution, here again you can see that the variable z depends on x and y. So let z equal to some capital X of small x into capital Y function of small y, or you can say that z equal to capital X into capital Y. So therefore your zxx will be x double dash into y, and zx will be x dash y, and zy will be x y dash. So by 1 we have x double dash y minus 2 x dash y plus x y dash equal to 0. So from here you can see that our y is common, so we will have x double dash minus 2x dash into y equal to minus xy dash. So that means x double dash minus 2x dash upon x equal to minus y dash upon y, and say their common value is k. So from here we will have x double dash minus 2x dash minus kx equal to 0, and y double dash plus small ky equal to 0. So now this equation can be written as d square minus 2d minus k of x equal to 0 and the second equation can be written as d dash of y plus k equal to 0. So for the first part, our auxiliary equation will be, now for the first part, this one, therefore d square minus 2d minus k of x equal to 0 implies auxiliary equation will be, replace your d by m, so this will be your, this is equal to 0. Therefore m equal to minus b plus minus b square minus 4ac, so this will be 4k divided by 2a. So that means we can write it as 1 plus minus under 1 plus k. So our x will be c1 e to power 1 plus under 1 plus kx plus c2 e to power 1 minus under 1 plus kx, and your y will be, here your auxiliary equation will be m plus k equal to 0, so your m will be minus k, so your capital Y will be, say c1 and c2 has been already used, so this will be c3 e to power minus k small y. Therefore solution is u equal to x into y. So we can write it as x is, this is your y multiplied by this x, c1 under 1 plus k of x plus c2 to the power minus 1 minus under 1 plus k of x. Now we can multiply this c1 and c3. So your answer will be u equal to some constant a, say c1 into c3, let us assume the constant c1 into c3 as a. So this will be your a e to power minus ky plus 1 plus under 1 plus k of x plus b e to power minus ky plus 1 minus under 1 plus k of x. So this is your solution of the partial differential equation.